I'm back. Okay, so we're picking up obviously with 3.10 solubility, and we've talked about the solubility idea already from multiple angles. So really, this is almost more of a recap with a few emphasis points going on there. So when we talk about solvation, okay, the ability to form a solution, there's three things that have to happen. Okay, we need to break apart the solute particles. So that means we have to at least loosen up their IMFs. We have to break apart the solvent particles, so we have to loosen up their IMFs. And then we need the solute and solvent to make their own attractions. So there's really three separate things that have to happen. And how soluble a substance is depends on how easily those combinations of things will happen. Oh yeah, by the way, like dissolves like. When a given solute and solvent have more similar IMFs, they will be more soluble. Why? Because it's going to be easier to pull them both apart because they have similar IMFs, and that's going to allow them to make new connections to each other as well. All right, so again, it comes down to those three things: pulling apart the solute, pulling apart the solvent, making new connections. When they're similar, that just makes it easier. So let's go to another extreme. Why don't water and oil form a miscible solution? Why are they immiscible? We know that water is a polar molecule, and oil, turns out, is a very nonpolar substance. They don't have very similar IMFs. The only thing that's really in common is London dispersion forces, and that allows a little bit of interaction between the two of them, but just not enough for them to grab onto each other. Okay, so it's really harder for specifically the oil to pull the water molecules apart. The water might be able to separate the oil, but the oil can't separate the water, and they're not going to make much attractions at that point then. So it's multiple things going on at once. And keep in mind, when we talk about these London dispersion forces, there is something, I mentioned it briefly, something we refer to as dipole-induced dipole or ion-induced dipole. If I have a nonpolar substance like an oil, and I bring something that's polar near it, okay, opposites attract, likes repel. So because this is polar, the electrons in this nonpolar substance start to come towards one side, and there's a repulsion, and the protons are, kind of shift a little bit, not so much really, but by relativity, they're more positive on this side. And so this becomes polar. So we get almost like a dipole-dipole attraction. And so they call it dipole-induced dipole attractions. And obviously, the same thing would be true if we took an ionic substance and put it by that nonpolar substance. Okay, the cation is going to cause the electrons to start moving that way, making this side relatively more negative, this side more positive, and it becomes a dipole of sorts. So there will be some attractions in that case, but again, the fact that an ion and a nonpolar substance are so different, there's really not going to be very strong attractions, even despite those ion-induced dipole attractions. We talk about water being a universal solvent, and please understand there is no universal solvent. Water is very good at dissolving things, but for example, why do we need to use soap? Because water isn't good at dissolving everything, okay? And we use the soap to help get the water to cling to different things, right? We talked about those amphipathic substances in one of the previous sections. So the types of attractions that are going on are going to make a significant difference here. And so we have to keep that in mind. So, a typical question: which of the following organic compounds is the least soluble in water? Well, we know water is polar. We know water has hydrogen bonding. Okay? So as I look, I see an OH here. I'm going to assume that means this is going to have some hydrogen bonding. I see an NH here. That's going to have some hydrogen bonding. I see an OH here. I know that's going to have some hydrogen bonding. And I see O's and H's. I don't know the formula. Even if I didn't know that glucose had hydrogen bonding, which it does, even if I didn't know it, I could reasonably say, because of the oxygens, that this is going to be a polar molecule. Now, when we come to octane, we're just talking about carbons and hydrogens, which are very close in electronegativity to begin with. And if we surround the carbons with all these hydrogens, it makes for a pretty nonpolar substance. And so octane would be the least soluble in water. Okay. So there is the structure of octane, or what's sometimes referred to as N-normal octane. You just see the very nonpolar, okay, very symmetrical. And yes, it's really more of a 3D molecule than that. But again, it's going to be very, very reasonably symmetrical. If so, we would say it's nonpolar. Most hydrocarbons are considered nonpolar, especially alkanes. All the other diagrams, like I said, showed the oxygens and hydrogens. So even if we didn't know for sure of hydrogen bonding, it's got to be polar. It's definitely more similar to water, which has the oxygens and hydrogens. So that's the kind of evaluation you need to do when you're thinking about solubility. Another short section. Done. Have a good one.